This video is going to be continuing our look at systems of linear equations, except instead of with equal signs, we're going to move into looking at systems of inequalities. So first we need to start with looking at inequalities themselves. We've already looked at solving them before, graphing them on a number line. But now we're going to look at what if it has two variables, an x and a y. How do I graph them on an x and y axis? What does a solution look like, and so on. So we're going to start with single inequalities first. So we have an inequality that means it has an infinite number of possible solutions. So in order to know if an ordered pair is a solution, means that if I plug in the x and the y value from the ordered pair, it satisfies the inequality, making it a true statement. So I'm going to look at this first equation here, or inequality I should say. 5x minus 3y is greater than or equal to 10. So I'm going to plug in 3 for x, 8 for y, and see if it satisfies the inequality. So I've got 5 times 3 for x minus 3 times 8. I want to know, is that greater than or equal to 10? So that says 15 minus 24 is bigger than or equal to 10. That is not true, so it is not a solution. Okay, let's look at B. I'm going to plug in negative 2 for x, negative 10 for y, and I want to know if that is bigger than or equal to 10. So I've got negative 10 minus 3 times negative 10, so that's going to be plus 30. Is that bigger than 10? Yes, so it is a solution. I want you to try C and D for next time. So now if we want to graph an inequality in two variables, we are going to graph the line like we've done in the past. But now, depending on the symbols, I decide whether the line is going to be dotted or solid. If you remember when we did them on the number line, we used either open, closed circle or parenthesis and bracket, representing whether it was strictly greater than or less than, or had the line underneath it. So the no line underneath is going to be a dotted line, solid line for if the line is underneath. What that means is that the line itself is or is not part of the solution, meaning if I choose a point that is on the line, if it is not or equal to, that point on that line is not considered a solution to the inequality. So let's take a look at the first one. We've got y is less than 2x plus 1. So I'm going to graph this as if it said y equals. So I'm going to graph 2x plus 1. So I'm going to go up 1 and then use the slope up 2 to the right 1. I'm just going to do that a few times to get a good line. And since it does not have a line underneath it, it's going to be a dotted line. Now, in order to know where all of my solutions are, I'm going to shade the region that makes this thing true. That means all of the points, x's and y's, so that y is less than when I plug the x in. If it is y is less than, I'm going to shade underneath the line. Those are all the values that make this true. How I know that, if I were to pick a point such as, how about 2, 1? If I were to plug that in, 1 in for y, 2 in for x, this is, in fact, a true statement. So all the points that fall within this shaded region make this inequality true. All right, if it's not already solved for y, I might like to do that so that it can make graphing easier. So I'm going to take this one and start solving it for y. So I'm going to subtract 3x from both sides. So that's going to be my negative 3x plus 8. Then I'm going to divide by 4y. The big thing I have to remember with inequalities is that if I multiply or divide by a negative number when I solve for the variable, I have to flip the symbol. In this case, I'm dividing by positive, so I don't have to change anything. So I get y is greater than or equal to negative 3 over 4x plus 2. So I'm going to graph that. 0, 2, and then down 1, 2, 3, over 1, 2, 3, 4. Then I'm going to go backwards, up 1, 2, 3, and to the left 1, 2, 3, 4. It has a line underneath it, so my line should be solid. And I have y is greater than, which means I'm going to shade above the line. That means all of the possible points that are above the line, or in this case on the line, those would satisfy my inequality. Let's look at a few more before we jump into systems of inequalities. All right, so I'm going to solve this A for y, so I'm going to subtract the 3 over first, so I've got 2y is less than negative 6 divided by 2. So I get y is less than negative 3. Y equals negative 3 is a horizontal line through negative 3. But since it's less than, I'm going to make it a dotted line. And it says all the y values that are less than negative 3. So that's below the line. Do one more. X is greater than or equal to 2. If I had x is equal to 2, it would be a vertical line at 2. And since it's or equal to, it stays solid, and I want all the x values bigger than 2. I want you to try these two for next class. So now, if I have a system of inequalities, it could be 2 or more inequalities, the solution region is going to be the shaded region that is overlapping for all of the inequalities. That means that those x and y values, those coordinate pairs, satisfy all of the inequalities. So we're going to graph each of them on the same set of axes and find where it overlaps. Let's look at a couple together. So I'm going to graph these two. I'm going to start with the first one, graph it in yellow. So I've got negative 5, and then it's down. I can't go down, so I'm going to go up 2 and to the left 1. Up 2 to the left 1, 2 to the left 1, and I'm just going to keep going. No line underneath, so I've got a dotted line. And it's y is greater than, so I'm going to shade above the line. For the second one, I'm going to graph in purple. I'm going to start at 3 and go up 1 into the right 1 and down 1 into the left 1. And this one is a solid line because it's got the line underneath. And its y is less than, so I want to shade underneath the line. Now what I notice is that the overlap is this region here. Any point that is on the purple line that's within that touches that region is considered a solution, but any of the points on the yellow dotted line that border the double shaded region would not be a solution. Anything that falls within the shaded region, for instance, the point 4, 0, would be considered a solution. Let's look at another one. Okay, the first one I'm going to solve it for y first. So I've got, if I subtract x from both sides, I've got negative x plus 4, divide by 2. And I'm going to graph that, and it'll be a dotted line. I'm going to go down 1 to the right 2, and do that several times, and then I'm going to go up 1 and to the left 2. Dotted line, and its y is greater than, so I'm going to shade above the line. Okay, then I'm going to graph in green the second one. So I've got negative 1 with a slope of 1. And this one has a line underneath, so I'm going to connect it with solid line, and its y is less than, so I'm going to shade underneath. And I see that my overlap is this region in here. These would be considered my solution set. Okay, I want you to try these two for next class. Okay, we're going to get a little bit more complicated and add in some absolute value stuff that we've done in the past two chapters. So the first, for example 3a, okay, the first one's just y, so I have a horizontal line through y equals 3, solid line, because it's or equals to, and it's all the y values that are less than. So it's underneath the line. Now I have absolute value, so I know the vertex for this absolute value is -4, and since there's no k, it's 0. So I'm going to plot -4, 0, 1, 2, 3, 4, 0. And then it has, since there's no number outside, it has a slope of 1. So I'm just going to go up 1 and to each side 1 and make my v. Now it has an or equals to, so it is solid. I wouldn't have a dotted v. And since I want all the values bigger, I'm going to shade above the v. So I notice that my double shaded region is this region in this triangle in between. Those are my solutions. And they include what's on this line and what's on the part of the v that touches that triangle that's shaded in. Alright, let's get slightly more complicated. Notice this absolute value does not have a y. So when we had absolute value of x equaled to solve, we would have done x equals 2 and x equals -2 and then solved. So I'm going to do the same thing with the inequalities, but I have to remember that when I solve, I have to flip the symbol when I make it negative. Okay, so I'm going to graph x equals 2. Oh, that's a little too far off. Let's try again. Sorry, guys. This is hard to do with this pen, apparently. Okay, that's going to be good enough. Okay, and I want all the values smaller than it. Then I want everything bigger than -2. That one went a little better. Okay, so right now the overlap is in between, but then I have this third line that I'm going to graph. So I'm going to start at 1, 2, 3, go down 1 and to the right 1, 2, 3, go up and to the left 3, solid line because it's got an or equals to, and I want all the values bigger than that line, so I'm going to shade above. So my overlap is going to be this region right here. I want you to try the next two. In example 4. And then for example, and I want you to try C. You have all 4 of these that you need to graph. So you need to find the region that is in between all 4 of them. And let's do D together. I've got 2 absolute value functions with y and x, so we've got a v that we have to draw. For the first one, my vertex is 3, 0, since there's no k value. 1, 2, 3, 0. It has a slope of 2, so I'm going to go up into the side on either side 2. Solid v, and its y is greater than, so I want all the values that are above the v. Okay, the second one, my vertex is going to be 3, 3. And it has a slope of -1, so I'm going to go down 1 into the side. And it should be solid as well. And I want all the values that are smaller than it So my overlap is going to be this little strange shaped region right here.